Now let's consider the case when the electric dipole is placed in a uniform 2D electric field. Now there are two terms associated with it. The first term is the uniform and the second term is 2D. Now let us first discuss that what is this 2D. The word 2D means two-dimensional axis. That is, in this condition we are talking about y-axis and the x-axis. Now I am talking about in this particular derivation about only this y and x-axis. Like for example a circle. When a circle is drawn like this circle that you can see on your screen, this circle is a 2D figure. But if I ask you to hold a globe, okay, so that globe of the earth represents the 3D figure with volume in it. For example, if you go on to watch a movie, okay, then all the movies comprises of a 2D figure. But in the special case, if we go and see any 3D movie, then you have some special glasses. Through that glasses, that picture appear raised to us. In that condition, you can see that all scenes are going near to you. That is, the scenes are coming near to you. Why it is coming near to you? Because in that condition, there is one third axis which is called a z-axis, and this z-axis is directed towards us. So in that condition it is called a 3D axis, that is 3-dimensional axis. But you don't have to consider the 3D in this condition, because now I am going to discuss about the 2D figure. Second is the word that is uniform. Okay, what is this uniform? Uniform means equal at every point. So now let's start with the uniform two-dimensional electric field. In order to show it, or in order to derive it, let me draw a diagram. This diagram gives you a pictorial representation of a uniformly distributed electric field. This is what? This is a uniformly distributed electric field. You can see here that at every particular point, if we draw any point, then at every point, this electric field is uniform. That is, it is all equal and equidistant from each other. So this is a uniform pattern, plus it is along y and x axis, so it is a 2D figure. So this is a uniform two-dimensional electric field. Now, if we have to place the electric dipole in this uniform electric field, then what happens? This is, suppose, an electric dipole. Okay, this is electric dipole. The 2 points are marked at, let's say, A and B. Point A, let's say, has a charge minus Q, and point B, let's say, has a charge plus Q. So this AB becomes an electric dipole. In this condition, the length of the electric dipole is given to you 2L. Now this AB electric dipole is placed in a uniform electric field, and you have to find the electric field intensity in this particular condition. Now this electric field dipole AB is placed in a 2D uniform field, and you have to work upon this concept that how is it going to resist in this particular uniform field. Now look at the diagram very carefully. If I ask you to draw a vector, then electric dipole is not a vector, so we have to represent it by a dipole movement. So this is a dipole movement, and the arrow points from negative towards the positive side. Now let us talk about every point one by one. Okay, in the case of point B, the charge at point B is plus Q. That means the force exerted at point B should be in the direction of the electric field, because the charge is plus Q. Plus represents that the force and the electric field are in the same direction. So this is the direction of the electric field. So that means the force at point B also heads towards the direction of the electric field. So this is the force which is exerted by plus Q charge at point B. Similarly, if I ask you what is the force exerted at point A, so at this point, that is minus Q, the force should be in opposite direction to that of the electric field. Why? Because the force should be negative and electric field is positive. So this denotes the force exerted at point A due to the charge minus Q. So this is F of minus Q. Now look at this diagram very carefully and you can see that the force is exerting at point B in right hand direction, and at point A the force is exerted towards the left hand direction. If I ask you from this figure that what is the net force exerted at AB, then your answer should be, it is 0. For example, if this is a point, let's say O, this electric dipole is making an angle theta with that of the electric field. If I ask you what is the net force at point O, so in this condition the net force should be F of plus Q minus of F of minus Q. Why it is negative? Because they both are in the opposite direction. So this net force calculated at a point O, this is a point O, is 0. So the net force along the electric dipole in this condition is 0. Now as the force at point A is going in this direction, at point B is going in that direction. So that means that the translatory motion in this condition is 0. What is this translatory motion? The translatory motion represents the motion in a straight line. If I ask you that one force is going here, one force is going there, so is this possible to have a translatory motion, that is a motion along a straight line? No. In that condition, there is no translatory motion. There should occur a couple movement, and this couple movement is called a rotatory motion. This rotatory motion generates a word which is very common, that is called a torque. So this torque is a very important word and we have heard it many times. In this condition, the torque is basically used to cause the rotational motion, or we can say so that it is the rotatory force. Like for example, if I talk you to spin the bottle over the table, in that condition, if you ever observe your finger and your thumb movement, that means the finger forces the bottle to spin downward and the thumb causes the bottle to spin upward. One at this side and the other at this side. Like for example, one in this direction and the other in this direction causes the bottle to rotate. So when such kind of action, that is two equal and opposite forces, when act upon any object, then it does not displace that particular object along a straight line. Rather than that, it causes a rotational motion, and when that rotational motion is produced, in that condition the force is converted into what we have written here, the torque. So now you can look here that at AB also this is the electric dipole F. This capital F is acting in this direction and this force is acting in this direction. That is, there are two equal and opposite forces acting along the electric dipole. So it does not cause the electric dipole to move along a straight line. No, in fact it causes a rotational motion that generates a torque. Now let's study what is the formula for torque. It is represented by tau. The formula for it is the force multiplied by the perpendicular distance, okay, the perpendicular distance between the 2 points that causes the force or that causes the torque. Now in this particular diagram, if I ask you to derive the torque, then first you have to derive the force. What is force? Force first is plus Q and the other is minus Q. Both have the same magnitude. We are not talking about the vector quantity, so the magnitude remains the same. Now, if you remember, then we have derived a formula for electric field intensity, that is E is equals to F upon Q. So from here, can we write F is equals to Q into E? Yes, we can write so that F is equals to Q into E. So now in this condition, it becomes plus QE, and in this condition it becomes minus QE. Now, if I ask you to write the magnitude of it, so it becomes Q into E. Multiply the perpendicular distance between the 2 points. What are the 2 points where torque is acting? One point is A and the other point is B. You have to find the perpendicular distance between A and B. Now, how to find the perpendicular distance between them? For that, we have to extend our diagram. Like for example, this and this. This is the perpendicular distance. Let's mark this point as K. Now you can see here B and K. B and K becomes a perpendicular distance between point A and B. So you have to measure the distance, that is BK. Now, how it is done? It is done by the same diagram that we used it. Now, referring to this diagram, you can see in triangle A, B and K. If this angle is theta, so according to the trigonometric rule, this angle also becomes theta. That is a corresponding angle. So that means angle BAK also equals to theta. Now, if we have to find BK, this side we have to find. So in that condition, you have to use one identity, that is sine theta. What is the sine theta? The sine theta is given by perpendicular upon hypotenuse. Now, the perpendicular in this triangle is BK. And what is hypotenuse? Hypotenuse is AB. Okay, BK you have to find. What is AB in this condition? AB is given to you. AB is given to you, that is 2L. The length between A and B is 2L. So from this particular identity, we get BK is equals to 2L sine theta. Now put this value of BK in this equation. Perpendicular distance between A and B is equals to what? BK. Now we have to put the value, that is 2L sine theta. So this is, we are calculating the torque. Now Q into 2L. This is what? This is the dipole moment. We already have talked about many times. So can we write here P into E sine of theta. So this becomes the formula for torque in the condition when the electric dipole is placed in a uniform 2D electric field. Now, concluding from this particular formula, we can write so that this torque is also called a restoring torque. What do you mean by restoring torque? The restoring is a torque that restores the original value. For example, if this is a vector, okay, one force is acting in this direction, other force is acting in this direction. That means it causes the dipole to restore its original position, okay. That's why it is also called a restoring torque. So the another name for this torque that is acting on the electric dipole is the restoring torque. Now, if we have to represent this formula in vector form, okay, in vector form, if I have to represent, then this turns into a vector sign on it, P cross E. So this is the formula when we consider this torque, that is a restoring torque in vector form. Now, this cross which you are seeing here, this is not a multiplication. Don't think so that P is multiplied by E. No, this cross basically represents a cross product. Okay, you have seen or you must have known about it that there are two forms of vectors, a cross product multiplication and a dot product multiplication. So in this condition, when there is a cross, then it represents a cross product multiplication, and when there is a dot, it represents a dot product multiplication. Now, this cross product multiplication has a particular formula, you know it, but let us give a quick revision. Now, if there are two vectors, let's say A and B, if there is a cross sign, that means they are undergoing through a cross product vector. So in that condition, it becomes AB sine of theta. AB sine theta becomes as the magnitude of A cross B. If suppose these are the two vectors and there is a dot sign in it, so it represents a dot product, and according to that, the formula for it is AB cos theta. Now, our concern is not a dot product, our concern is a cross product. So if you want the magnitude of this vector form, so what is the magnitude? The magnitude of this torque is P into E sine of theta. Now, the vector form has two identity, that is a magnitude and a direction. Magnitude is known to you, but what about the direction? So, there is another concept, that is a direction in a vector quantity. How the direction is found? In the case of cross product, the direction is found by a very famous rule which we call right hand screw rule. The right hand screw rule is used to find the direction of any vector quantity which is given in a cross product. So now let's see what is this right hand screw rule. Now, according to this right hand screw rule, we have to find the rotational motion, or it gives us the direction in case when there is a rotational motion of force acting on a body. The right hand screw rule indicates if suppose we are holding a screw with our right hand. Suppose this my pen, okay, this pen is a screw and this is my right hand. So I am holding my pen like this. Okay, this is how we hold a pen or simple objects if we have. So in this condition, you can see my fingers totally curl a pen and my thumb is pointing in the direction of this cap. So according to the right hand screw rule, this curling of the fingers is done in the direction of the electric field, and this thumb point to the direction of the force that act upon the rotational object. So this is about the right hand screw rule. But if I ask you to implement this right hand screw rule in the case of a vector, that is when we are talking about the cross product, then the rule changes slightly. In this condition, let me refer a diagram. This is my diagram and I have to find the direction of this vector quantity by using the right hand screw rule. Now, let us proceed one by one. Look at the diagram. AB. AB is a line that represents a dipole movement and it is somewhat slant. Okay, it is making an angle theta with that of the electric field intensity. Now, according to this rule, we have to stretch our palm of the right hand. This is how I stretched my palm. Now, the fingers that are stretched, these fingers point in the direction of the first vector. According to this formula, what is your first vector? The first vector is a dipole movement, that is P. So in this diagram, the dipole movement is along the line AB. So we have to point a stretched finger in the direction of AB like this. Okay. So this is how I point my fingers in the direction of AB. Now, this thumb should be at 90 degree with that of the stretched fingers. Now you have to check the direction of the thumb. In this condition, we have two directions. If I point my stretched finger in the direction of AB in this direction, so my thumb is pointing towards my side, that is going out of the plane. But in this condition, there is another form, that is if suppose I point my stretched finger like this. This is also one way in which I can point my fingers along the line AB. So this is how I am pointing my finger along the line AB. So where my thumb is pointing? My thumb is pointing towards your side, that is into the plane. It is going into the screen. So that means there are two ways, but you will be confused that which way we have to go. In that condition, the right hand screw rule tells that the curling of the finger should be in the direction of the second vector, and that too along a smaller angle. Now, let us look here. If suppose this is how I point my finger along the direction AB. Okay, this is how I point. If I curl my finger, you can see this is how I am curling my finger. So I am curling my finger towards the electric field intensity. So this AB vector is making an angle theta with that of the electric field intensity. So you can see that this theta is very small. So it is advisable for me to curl my finger in this direction because the theta is very small between AB and the electric field intensity. If suppose I reverse the direction, if I suppose I do my finger like this. So this is the direction in which my fingers are curling. So you can see here that this becomes a greater angle for me to cover the second vector, that is the electric field intensity. So why I should go for larger angle? The rule states that you have to follow the smaller angle of the second vector. So my smaller angle is pointing in this direction. So that means I have to curl my finger in this direction. So this is how we need to curl the finger. But where your thumb is pointing? The thumb is pointing into the plane. You can see my thumb is pointing into the screen, that is going towards your side. From my point of view, if you see that the thumb is pointing towards your side, that is into the plane, into your screen. So that represents the direction of the torque. In this condition, what is the direction of the torque? The direction of the torque is into the plane. Now, how we represent it? We represent it by a sign that is a cross. If we mark a cross sign, this cross sign represents that this torque is going into the plane, that is into this particular screen. So this is how the vector is represented. If suppose I talk that the torque is going out of the plane, so what is the representation? It is shown by a dot. This is how it is represented. It shows you out of the plane, and the cross with a circle on it represents into the plane. So this is a very important topic for you to understand, that how this right hand screw rule is used to find the direction in the case of a vector quantity.